All right, welcome to your first screencast for our early and modern atomic theory unit. During this unit, we are going to cover everything from atomic structure and isotopes and ions, how the model of the atom has changed over time, so what we used to think it looked like to what we currently think it is with the wave mechanical model or the quantum mechanical model. We will talk about the quantum mechanical model, quantum theory. We'll also cover the periodic table because it directly relates to the structure of an atom, as well as valence electrons, the octet rule, and periodic trends. Some of this you'll find should be a review. There are some things that we're going to learn that are completely new, but a lot of this you did already learn in physical science. So hopefully this won't be quite as confusing to you as what previous material might have been. So for our first one here, the atomic structure and isotopes for your first guide sheet or your guided notes handout, we're going to cover slides 1 through 12, and this is your essential question. What are the three types of subatomic particles, and how do they relate to the atomic number and atomic mass of an atom, an ion, and or an isotope? So there's a lot in that essential question. Not only what are the three types of subatomic particles, but how do you determine the atomic number and the atomic mass for an atom, an ion, and an isotope? And hopefully by the end of this discussion, you'll be able to answer that. So I'm going to go ahead and switch over here and get started on our PowerPoint. So like I said, we're going to go through slides 1 through 12. So this is the structure of the atom and the periodic table, kind of all in one. So electrons, protons, and neutrons, these are the subatomic particles. So when we talk about what is an atom made out of, atoms consist of these three primary particles, protons, neutrons, and electrons. The nucleus is a small, dense, positively charged region in the center of the atom. When they first discovered the atom, they did not know that there was a nucleus. So you're going to see that Rutherford is credited with discovering this nucleus during his gold foil experiment in the next couple of lessons as we go through how the atomic model has changed. But today we do know that there is a nucleus, and that nucleus contains the protons, which are positively charged, and the neutrons, which are uncharged. So the nucleus itself has a positive charge. Electrons are the negatively charged particles, and they're located outside the nucleus of the atom. One thing that's really interesting about electrons is once Rutherford really discovered the structure of the atom as far as where the protons were and the nucleus, then it became trying to figure out where the electrons are. And we're still trying to figure out where electrons are. This is kind of the basis for the modern atomic theory, is dealing with electrons. So you'll see us cover the Bohr model of the atom, but then we're going to take it a step further to the quantum mechanical model, which you might not have ever heard of before. So we will study the electrons in rings, but we will also study the electrons in their true orbitals outside of the nucleus. So what's also cool or interesting is the protons and electrons have opposite charges. So a proton is positive, and to have an opposite charge, an electron would be negative, and they are equal in magnitude, meaning that they count the same. Even though a proton is like 1,000, I believe it's 1,737 times bigger than an electron. Even though it is so much bigger than an electron, we still say that they both count as one because that positive and negative charge has to balance out. So we say that a proton is +1 and an electron is -1. A neutral atom, so by definition, if you see the word atom, by definition, it means that there's no electrical charge. So if you know the number of protons, then you know the number of electrons. So if we look at the periodic table and you look at any of those atoms on the periodic table, so like beryllium, for example, is number 4. That number 4 tells me that it has 4 protons. If I say it's an atom, then it's going to have 4 electrons also. So the electrons and the protons are going to be the same. If it's an ion, they're not going to be the same. So in a positive ion, you are going to have more positives, so more protons. In a negative ion, you are going to have more electrons. You're going to have more of your negatives. You will see that something can never gain or lose a proton, at least in these types of basic chemical reactions and these types of relationships. So our proton number is never going to change. You're going to see things gain or lose electrons and gain or lose neutrons. So another thing that should look somewhat familiar to you is isotopic notation. That's what this is right here. When you're dealing with isotopic notation, it's just a way of writing all of this information that we know about an atom, ion, or an isotope in a way that just allows you to put all this information in a nice, neat way. So the mass number is the number that's going to go on top. Mass number is the sum of the protons plus the neutrons. So how do you find the mass of an atom? Well, you take the protons and the neutrons and you add it together. So if I have 5 protons and 5 neutrons, my mass is 10. The atomic number is the number that you're going to put on the bottom. That is the number of protons. If you know the element you're working with, all you have to do is look on the periodic table, because that number, the 1, 2, 3, 4, 5, 6, 7, all the way up through 118, that number tells you how many protons are in the nucleus of that atom. So that is the atomic number. And then we put the symbol of the atom here. And you might also notice the charge, there isn't a spot up here for it, but this is where you would write the charge of an ion. So if something had a 2+ charge, you would put a 2+ up here. If something had a 3+ charge, 3+. If it was a 1-, you'd put a 1- up there. So when you dealt with ions in physical science, we always put the charge in this top corner. So here's a little table that's going to show you the basic characteristics of the electrons, protons, and neutrons. So in terms of the size, the electron is by far the smallest one. As far as mass goes, electrons don't even count as having mass. Their relative mass is 0. We count protons and neutrons both as 1, even though neutrons are slightly heavier in terms of their atomic mass units. Neutrons are slightly heavier, but we still count them as 1. You'll notice this is their actual mass in grams, like if you were to weigh it on a scale. You'll notice that protons are a little bit lighter than neutrons. So even though they're almost the exact same, it relates to this relative mass in terms of AMUs, which is what's recorded on the periodic table, as we go ahead and count them as 1, even though it's not quite the same. But we do count electrons as having a 0 mass. So when you look at the mass of an atom, which is protons plus neutrons, you don't even take electrons into account. Electrons do play into charge. So electrons are all given a -1 charge. Each electron counts as a 1-, and each proton counts as a 1+ charge, and neutrons have no charge. That's why they're called that, for neutral. So if we were to go through and do these examples of calculating the number of protons, neutrons, and electrons in each of the following, I think we'll go ahead and review these in class, but I want to make sure that I kind of go through how to do this, and we'll see if you guys can figure out the second one. So if we remember, the top number is mass, the bottom number is the number of protons. So how many protons does this have? Well, it's boron. It is number 5 on the periodic table. That tells me it has 5 protons. There's no charge up here, so that tells me the number of protons and electrons have to be the same. So there's 5 electrons. Now for kind of the trickier one, if I know that protons plus neutrons is 11, I have 5 protons. How many neutrons do I have to have? Well, 5 plus what equals 11 is 6. So I have to have 6 neutrons in this atom. So go ahead and see if you can figure out what the protons and neutrons and electrons are, and we'll review that part in class. So talking about neutrons brings us to a discussion about isotopes. We're going to talk about ions a little bit more later, but we're going to go ahead and go through isotopes. What is an isotope? Isotopes are when you have atoms of the same element, but they're going to have different masses. So here I'm showing you 3 atoms of hydrogen. And what's different among them is the mass. You can see that top number. The first one has a mass of 1, the second one has a mass of 2, and the third one has a mass of 3. And if you look in the nucleus, this one shows that it has 1 proton. This one shows that it has 1 proton and 1 neutron. and this one shows that it has 1 proton, and it still has 2, or it has 2 neutrons. So for a total mass of 3, a total mass of 2, a total mass of 1, these are all 3 still considered hydrogen. They're just hydrogen isotopes with a different amount of, with different neutron amounts. So they contain the same number of protons, but they contain different numbers of neutrons. That is what makes something an isotope. By definition, that is an isotope. So isotopes of the same element are going to have identical chemical properties. So all of those isotopes of hydrogen are all going to react the same way. They're all going to have the exact same chemical properties. They're all going to go through the same types of chemical reactions. You wouldn't be able to tell one hydrogen from the other. The only way that you can is by calculating the actual mass, by getting the mass of it. As you guys had learned in biology, some isotopes are radioactive, like carbon-14 is radioactive. If you look at chlorine on the periodic table, and you go through and you find what is chlorine, well, it's number 7. So what's its atomic number? It is number 17. So it is atom number 17. That means that it has 17 protons in its nucleus. The mass that's given is 35.45 or 35.453, what might show up on your periodic table. Do you notice that this mass is not an exact number? You would think if you were adding protons plus neutrons, whole numbers, you would get a whole number. Well, the mass that's on the periodic table is not the mass number for an isotope. It's actually a weighted average. So the mass that's given on the periodic table is called the atomic mass. When we talk about that top number in isotopic notation, that's just protons plus neutrons. That is the actual mass number. So there's a little distinction between the two. So what is atomic mass? This is what's given to you on the periodic table. The atomic mass is the weighted average of all the masses of all the isotopes that make up chlorine. So chlorine consists of chlorine 35 and chlorine 37. So if you were to find chlorine in nature, about 75% of it would be chlorine 35, and about 25% of it would be chlorine 37, meaning this would be the one that has protons plus neutrons equals 35, protons plus neutrons equals 37. So when you determine that atomic mass, there's just a formula that allows you to do this. You find a weighted average. Instead of a regular average, where I would take 35 plus 37 divided by 2, in a regular average, that's going to put a weight of 50% on both of these. We're going to find a weighted average. I don't want them to have equal weightings. I want chlorine 35 to account for 75%, and I want chlorine 37 to account for about 24.23%. So I need to do my average a little different. So the first thing that you're going to do in all of these is convert the percentage to a decimal fraction. So instead of 75.77%, I'm just going to say 0.75, and instead of 24.23%, I'm going to say 0.24. So you convert it to decimals, which is exactly what I have shown you right here. Feel free to pause and write this stuff down as needed. So all I did was just divide by 100 because percents are based out of 100. Then I'm going to multiply the decimal fraction by the mass. So if 75% of it was chlorine 35, that's what I'm going to multiply it by. So that means out of the total mass, 26.5 AMUs of it is going to come from this amount of chlorine. And I take 0.24 times 37, and I get this to have a mass of 8.97. I get this to have a weight of 8.97. So what this is showing me is if I wanted to do a regular average, this would have been 50% and that would have been 50%. That's why I can add them up and divide by 2. But in this case, I don't want them to be equal weighted. I don't want them to have the same weightings. So I want this one to have more weight than this. And that's what I'm calculating with a weighted average. It's the same way your grades are calculated. And then I'm going to add the mass contributed by each isotope. So I'm going to take those two masses, 26.5 plus 8.97, and I get a mass of 35.5, which is, ironically enough, what's on the periodic table. So I want you to try this practice problem. We will go through it in class. We will review this, and we're going to do some more practice with weighted averages in class. But this one, I want you to try to solve the neon problem. And you can pause as needed.